Hello everyone. In the last video, we have seen several properties of Fourier transforms. Okay. Now let us see one more property. Let fx be continuous and f dash of x be piecewise continuous on minus infinity to infinity. Further, let integral from minus infinity to infinity mod of fx dx strictly less than infinity. In other words, this is finite or it converges. Okay, and integral from minus infinity to infinity mod of f dash of x dx is also converging. That means this quantity is also finite. Then Fourier transform of f dash of x is given by I into alpha into f of alpha, which is the Fourier transform of the function f of x. Okay. Note that when we showed the existence of Fourier transform for the function f of x, these were the same conditions that were imposed for the function f of x. Now we want to talk about the Fourier transform of the function. Let us suppose say g of x, wherein that g of x is the function f dash of x. Okay, so therefore these conditions should also be true for them, for that f dash of x, to talk about the Fourier transform of the function f dash of x, and hence it is given here f dash of x be piecewise continuous and this quantity be finite. That means this integral converges. And now we are talking about the Fourier transform of the function f dash of x. Okay, let us try to see how this property is. Fourier transform of f of x is given by 1 upon root of 2 pi integral from minus infinity to infinity f of x e raised to I alpha x dx. So the Fourier transform of f dash of x will be 1 upon root of 2 pi integral from minus infinity to infinity f dash of x e raised to I alpha x dx. Okay. So here we will get 1 upon root of 2 pi e raised to I alpha x f of x from minus infinity to infinity by using integration by parts formula. This will be I into alpha e raised to I alpha x f of x dx. Okay, we have said that Fourier transform is equal to this provided f of x goes to 0 as x goes to plus or minus infinity. So as here this quantity will vanish because f of x will go to 0 as x goes to plus or minus infinity, and we will be left with minus I into alpha. This 1 upon root of 2 pi factor will remain there, and integration from minus infinity to infinity. Okay, so this will be minus I into alpha e raised to one upon the root of 2 pi integral minus infinity to infinity f of x e raised to I alpha x dx. This is the Fourier transform of the function fx. So we get I into alpha into f of alpha, this. Okay. Now let us generalize this statement. Here we have seen only for the first derivative. So if we have the rth derivative, or you can say nth derivative, how the generalization will be. So we have the fifth property. if f of x and its first n minus 1 derivatives are continuous and if its nth derivative is piecewise continuous, then Fourier transform of you can see here the nth derivative will be given by minus I into alpha raised to n into Fourier transform of fx alpha. So this, in other words, I into alpha raised to n into f of alpha, where f alpha is the Fourier transform of the function fx, provided f and its derivatives are absolutely integrable we also assume that f of x and its first n minus 1 derivatives vanish as x goes to plus or minus infinity. We are talking about the Fourier transform of nth derivative of the function f of x, which will be given by this. Okay. So from the definition of Fourier transform, what do we have? For the nth derivative, this will be given by 1 upon root of 2 pi integral from minus infinity to infinity nth derivative of fx e raised to I alpha x dx. If we use integration by parts, before going to that, let us introduce one notation to denote the Fourier transform of nth derivative of the function. Okay, so this will be Fourier transform of the, so this will denote Fourier transform of nth derivative of the function f of x. So now let us use integration by parts for this. What we will get is 1 upon root of 2 pi integral from minus infinity to infinity into e raised to I alpha x minus infinity to infinity minus integral from minus infinity to infinity e raised to I alpha x into I alpha into f n minus 1th derivative into dx. So 1 upon root of 2 pi. We have assumed that fx and its first n minus 1 derivatives vanish as x goes to plus or minus infinity. So this is the n minus 1th derivative of the function fx. X is going from minus infinity to infinity. So this quantity will vanish and we will be left with minus I into alpha into 1 upon root of 2 pi integral from minus infinity to infinity f n minus 1 x e raised to I alpha x dx. Okay, from here it is clear that this is the Fourier transform of n minus 1th derivative of the function f of x, of this function. This is the Fourier transform of this function, which we have denoted it as this of alpha. This was for the nth derivative, this is for the n minus 1th derivative. We assume that in the next step we will be getting fn minus 2th derivative of the function f of x, and all those will go to 0 as x goes to plus or minus infinity, that we have already said here. Okay, so accordingly what we will get is Fourier transform of nth derivative. We have got it as minus I alpha into f n minus 1 alpha minus I alpha square will be for n minus 2 alpha minus I alpha cube will be f n minus 3 alpha, and accordingly, so in the last what we will get is minus I into alpha raised to n into and hence the Fourier transform of the nth derivative of function fx will be minus I alpha raised to n into this f alpha. Now, as we have seen already, the Fourier transform of the function f dash, that is the first derivative, will be minus I alpha raised to 1 into f alpha. This is what we have already seen here, into f alpha. Let us look at one example. Find Fourier cosine transform of e raised to minus a t square. The function is given as e raised to minus a t square. From the definition of Fourier cosine transform, we have root of 2 upon pi integral from 0 to infinity f of t cos of alpha t dt. This will be root of 2 upon pi integral from 0 to infinity f of t is e raised to minus a t square into cos of alpha t dt. This is the Fourier cosine transform. Okay, Let us suppose say this is equal to I. Okay. Now differentiating above equation with respect to alpha, we get this will be, you can see here, this will be the function of alpha, and so we are differentiating it with respect to alpha. This I will be a function of alpha. So when we differentiate it with respect to alpha, we get root of 2 pi integral from 0 to infinity. We want to differentiate this with respect to alpha. Okay, so by using the Leibniz rule, we will have to differentiate this. So differentiating it with respect to alpha. So take it inside and partially differentiate this function with respect to alpha. So what it will be? Here we have this, which is a function of alpha. So that will become minus sine alpha t into t into e raised to minus a t square, this dt, plus by using the Leibniz rule, okay, in this function when there is t, we have to put infinity, substitute the upper limit into the derivative of the upper limit, minus in this function substitute the lower limit. So when you put t here, t equal to 0, for t equal to infinity, this is minus, so it will be 1 upon e raised to that, so that term will go to 0, minus if you put 0 in place of t, this will be 1 and this will be 1. So we will be left with into derivative of this, so all the further terms will vanish and we will be left with only this. Okay, this is by using Leibniz rule. Integral from 0 to infinity minus t sine of alpha t e raised to minus a t square. Okay, so if I manipulate this, multiply by 2a, divide by 2a and multiply by 2a. So here 1 upon 2a into root of 2 pi integral from 0 to infinity, this minus 2at, I can e raised to minus a t square into sine of alpha t dt. 1 upon 2a root of 2 pi integral from 0 to infinity. You can see here this is the derivative of e raised to minus a t square. Okay, the derivative of this into sine of alpha t dt. So again, if we use integration by parts, what we will have is root of 2 by pi e raised to minus a t square into sine of alpha t minus integral of alpha cos of alpha t into e raised to minus a t square dt. Here it is from 0 to infinity. 1 upon 2a root of 2 upon pi. The limits are from 0 to infinity. Okay, so clearly this with infinity it will go to 0. Also for 0, sine of 0 is 0, so this will go to 0. Minus, we will be left with this. So minus integral 0 to infinity alpha cos of alpha t e raised to minus a t square dt. 1 upon 2a, if you observe this, this is nothing but again this I. Okay, root of 2 by pi, except this minus sign, integral from 0 to infinity cos of alpha t e raised to minus a t square dt, and this is alpha. So this is nothing but minus alpha into this I. So now we have got the equation minus alpha I upon 2a. If you solve this differential equation, this is differential equation, so di divided by this I and minus alpha by 2a into this d alpha. If you solve this integral differential equation, you will see that I is equal to, let's take the constant as some c, into e raised to minus alpha square by 4a. Okay, this differential equation can be solved by taking this di by I. It will be minus alpha by 2a into d alpha. You integrate from both sides, that will be ln of I minus alpha square by 4a into the constant c, which can be manipulated, and then you get e raised to this. So I is equal to c into this. Now we will have to find the value of this c. Okay, so if we take alpha equal to 0, for alpha equal to 0, what will happen? C is equal to, in I, if we put alpha equal to 0, what we will get? Root of 2 pi integral from 0 to infinity e raised to minus a t square dt. Root of 2 pi integral from 0 to infinity e raised to minus a t square dt. Okay, let us evaluate this integral. Integral from 0 to infinity e raised to minus a t square dt. We'll use the substitution. A t square is equal to some x, so t is equal to x raised to half by root of a. So dt is equal to half 1 upon 2a x raised to minus half, and the limits will remain the same. Yes, so with this substitution, what do we get? Integral from 0 to infinity 1 upon 2 into root a x raised to minus half into e raised to minus x dx. Again 1 upon 2 root a integral from 0 to infinity x raised to minus half e raised to minus x dx. Again, this is the function, gamma function. So 1 upon 2 root a, the value of this gamma half will be root of pi. So this will be the value of this integral. So if we substitute it here, what we will get is root of 2 upon pi into 1 upon 2 root a into this root of pi. So 1 upon root of 2a is the value of c, and hence I is equal to 1 upon root of 2a into e raised to minus alpha square by 4a. Therefore, the Fourier cosine transform of the function e raised to minus a t square will be 1 upon root of 2a into e raised to minus alpha square by 4a. Fourier cosine transform of this function is this. This I, we have already assumed that this we had considered it as I, and now we are getting I equal to this, which is nothing but the Fourier cosine transform of this function. Let us look at one more example. Find Fourier transform of this function. By using the Fourier transform formula, we will have one upon root of 2 pi integral from minus infinity to infinity f of x e raised to I alpha x dx. Clearly from the definition, this will get reduced to integral from minus 1 to 1 into e raised to I alpha x dx, which is equal to 1 upon root of 2 pi. Here we will get e raised to I alpha x by I alpha minus 1 to 1. So that is equal to 1 upon root of 2 pi e raised to I alpha minus e raised to minus I alpha divided by I into alpha. Okay. Now by using the Fourier transform of this function, let us try to find what is the value of this integral. Okay. So this will be nothing but if I divide by 2 and multiply by 2, what I will get is root of 2 upon pi into this will be 1 upon alpha into sine of alpha. This is the Fourier transform of given function. Now by taking the inverse Fourier transform, we will have root of 1 upon root of 2 pi integral from minus infinity to infinity f of alpha into e raised to minus I alpha x d alpha. Okay. see here, f of alpha is equal to this, and if alpha is equal to 0, then the value will be root of 2 by pi. Okay, if alpha is 0, then you find the limit as alpha goes to 0. For this, the answer will be root of 2 by pi. Okay, by taking inverse Fourier transform, fx is equal to this. That means 1 upon root of 2 pi integral from minus infinity to infinity f alpha, which is root of 2 pi sine alpha by alpha into e raised to minus I alpha x d alpha which is equal to f of x. So this is 1 upon pi, root 2 will get cancelled, integral from minus infinity to infinity sine alpha upon alpha into e raised to minus I alpha x d alpha equal to f of x, which is defined by this. For x equal to 0, we will get 1 upon pi integral from minus infinity to infinity sine of alpha by alpha. For x equal to 0, this will become 1 into d alpha, and it will be equal to f of x. At x equal to 1, it will be 1. And if you note that this is an even function, and hence it will be integral from 0 to infinity sine of alpha by alpha d alpha is equal to 2 upon pi equal to 1. So if I take it on the other side, this will be equal to pi by 2. You can note down this value and keep, because many places in applied mathematics this integral is used. So integral from 0 to infinity sine alpha by alpha d alpha is equal to pi by 2. In complex analysis, you can find a nice proof of this integral. That means why this integral is equal to pi by 2. The proof is done by using the complex exponential form of sine of alpha. Okay. So we have seen that Fourier transform can also be used to evaluate the value of different integrals. Like the same way how we use also the Fourier integral formula.